Hello everyone, a very good evening to all. Myself, Vivekananda Naik. I am a PhD research scholar in the Department of Energy Science and Engineering, IIT Delhi. I welcome you all once again for this interaction session on solid state physics. This is our eighth interaction session. The course is being flowed this July 2024 session by NPTEL with course code NOC24 PH43. So today we will discuss a few problems that will basically cover the concepts of physics of semiconductors and the band theory of solids. So let's start with the first problem of the day. The question says the collision time for electron scattering in pure silver, which has a Fermi energy of 5.5 electron volt at 300 Kelvin, is 10 to the power minus 14 second. The mean free path of electron is option A 1.19 into 10 to the power minus 7 meter. Option B 1.39 into 10 to the power minus 8 meter. And option C 3.49 into 10 to the power minus 9 meter. And option D is none of these. So the question says we need to find the mean free path. So we need to find the mean free path, that is lambda, where lambda is the mean free path, and what is given to us, we are given with this is the silver atom, and for silver atom at 300 Kelvin, the Fermi energy is given to us. Fermi energy is 5.5 electron volt, and the collision time for electron scattering, that is tau, is given 10 to the power minus 14 second. So we need to find out the mean free path. We are given with the collision time and the Fermi energy of silver at 300 Kelvin. So this type of problem also in last class we have also solved a few problems like this. So I'll give you a few minutes to try this question and then I will discuss how this will be solved and what is the correct answer. So if we solve it, we know if Fermi energy is given as EF, then we can relate the Fermi energy with Fermi velocity. Because if you see in the question, we have the collision time tau, and in order to find the mean free path, we need Fermi velocity. So, if EF is the Fermi energy, then it can be written in terms of Fermi velocity as EF is equal to half mvf square, where m is here mass of electron, which is 9.1 into 10 to the power minus 31 kgs. So, from this equation, we can write V is 2 EF by me root over. So, which if we calculate, it will be EF, we know EF is 5.5 electron volt. So, in order to convert into joule, it will be 5.5 into 1.6 into 10 to the power minus 19 joule. Then mass of electron we also know 9.1 into 10 to the power minus 31 kg. That implies Vf will be 2 into 5.5 into 10 to the power minus 19 into 1.6 divided by m is 9.1 into 10 to the power minus 31. So if you calculate it, it will be 1.39 into 10 to the power 6 meter per second. So since we have V, so the mean free path, the mean free path of electrons lambda will be tau into V. So tau is given to us. Tau is 10 to the power minus 14 second. So 10 to the power minus 14 into 10 to the power 6 into 1.39, which will give us 1.39 into 10 to the power minus 8 meter. So if you see the options, option B will be the correct option, that is 1.39 into 10 to the power minus 8 meters. I hope this is clear to all of you. So basically in this question, what we do, what we did, the Fermi energy was given to us. From that Fermi energy, by putting the formula EF is equals to half mvf square, we calculated the Fermi velocity. And since velocity and collision time is given, we can easily calculate the mean free path, which is the product of collision time and Fermi velocity. So the correct answer is 1.39 into 10 to the power minus 8 meter. So we'll move to the next question. The question says the probability of occupation of an energy E, where E minus EF equals to KT, is given by option A 0.27, option B 0.57, option C 0.63, or option D 0.73. So we know electron is a Fermi particle or fermion, and since their Fermi particles are indistinguishable quantum particles, so they obey Fermi-Dirac distribution function, and according to the Fermi-Dirac distribution function, they have a particular probability distribution function which uh, indicates the probability of occupation of an electron in that particular energy level. So we have a formula which is called as probability of occupation. That is P, which is a function of E, is given by 1 by 1 plus exponential E minus EF by kBt, where EF is the Fermi energy, E is the energy of a particular state, or energy of a particular level in which we are calculating the probability. Then Kb, we all know Kb is Boltzmann constant and T is the temperature. This P is the probability of occupation. So these are the four options. You just need to put the condition, and the condition is given to us, that is E minus EF equals to KBT. So if you put the condition, you can easily calculate what will be the probability of occupation. So I'll give you a few minutes to calculate and and decide whether option A or option B or option C or option D will be correct. So if you calculate PE, then P is 1 by 1 plus exponential E minus EF by KBT. So given that E minus EF equals to KBT, so PE will be 1 by 1 plus exponential kbt by kbt, that is 1 by 1 plus e to the power 1, that is 1 by 1 plus 2.71, which is approximately 0.2689 or 0.27. So the correct option is option A, that is 0.27. So the probability for an energy level for which the difference in that energy level to the Fermi energy is equals to kBt, then the probability of then the probability that the electron will be present in that state is 2.27 or 27%. So all these phenomena um, are due to the quantum mechanical behavior of electron. Can say so. Let's move to the question number 3. The question says, find out the degrees of degeneracy of the quantum states corresponding to 9 for the sum of the squares of the quantum numbers nx, ny, nz in the free electron model. So we need to find out the degeneracy of that level of that state for which the sum of squares of the quantum numbers, that is nx, ny, and nz, is 9. The options are option A 3, option B 6, option C 9, and option D 11. So I'll give you a few minutes to try this question. I have also discussed similar type of questions in previous sessions also. So please try this and I will explain after a few minutes. So this question is based on the free electron model, and according to free electron model, the electron inside the electrons in a solid are uh, considered to be confined in a three-dimensional infinite potential box. And if we uh, calculate the energies, then the energies for each level depends upon the squares of the sum of the squares of quantum numbers nx, ny, and nz. So the energy given by h square by 8 ma square nx square plus ny square plus nz square. So the question says, what is the degeneracy for which the sum of the squares of quantum numbers nx, ny, nz is 9? So each nx, ny, nz can have values 1, 2, 3, 4. So, but it can't have values 0, because if nx, ny, nz, any one of them is 0, then the wave function corresponding to that state will be 0. Because if you see the wave function is psi nx, ny, nz is 2 by L sine nx nx pi x by L into 2 by L root over sine ny pi y by L into 2 by L root over sine nz pi z by L, where L is the length of the three-dimensional potential box along x direction, y direction, z direction. So you see, if any one of these components, that is nx or ny or nz, is 0, then this will be 0, which indicates there will be no particle present in that state. So nx, ny, nz can't have 0 values, they have only non-zero values. And we here need to find out the level for which nx square, ny square, nz square is 9. So suppose nx is 1, ny is 1, nz is 1, then nx square plus ny square plus nz square will be 3. Then how we will get the sum 9? Then for sum 9, either nx is 1, ny is 2, nz is 2. So this will give us nx square plus ny square plus nz square equals to 9. 4 plus 4 plus 1, 9. Also, here we need to find out the degeneracy. So degeneracy means the different levels which have same energy, but they have different wave functions. So since the wave function depends upon the value of nx, ny, nz, but the energy depends upon the sum of nx square plus ny square plus nz square. So if we change the value of nx, ny, nz, but the sum remains fixed, then those states which have same energy but different values of nx, ny, and nz, they are called degenerate states. So one case is nx equals to 1, ny equals to 2, nz equals to 2. So next also, this is fast. Again, if nx equals to 2, ny equals to 1, and nz equals to 2, in that case also, it will be 9. And again, this is question scenario 2. And again, if nx equals to 2, ny equals to 2, but nz equals to 1, then in that case also, nx square plus ny square plus nz square will be 9. So there are three different combinations of nx, ny, and z for which the sum of the squares remains same, that is 9. So the correct option here in this question will be option A. So the degrees of degeneracy for the sum of 9 is 3. However, if you see here, since only there are two twos and only one one, so if we consider another case for which nx equals to 1, ny equals to 2, and nz equals to 3, so in this case, the sum is nx square plus ny square plus nz square is 1 plus 4 plus 9, that is 14. So you see, since here nx, ny, nz, all three has different values, so there will be three factorial combinations for which this sum will be same. So which is 3 into 2, that is 6 ways, or there are 6 combinations of nx, ny, nz for which the wave function is different, but their sum is same. So since the sum of the squares are same, the energy will also be same. So if in the question it was given, if the quantum size corresponding to 14, then in that case, the correct option will be option B, that is 6. So there will be 6 degenerate states for which the sum of squares of quantum numbers will be 14. So I hope this is clear to everyone. Now we will move to the next question, that is question number 4. The question says, calculate the Fermi energy of electron at 0 Kelvin for a metal with electron density of 10 to the power 28 per meter cube. Options are option A, 1.12 into 10 to the power 21 joule, 2.75 into 10 to the power minus 19 joule, 3.11 into 10 to the power minus 11 joule, and option D, 4.26 into 10 to the power minus 9 joule. So I'll give you a few minutes to try this question, and then I will discuss how I will solve it. So in order to calculate the Fermi energy of electrons, there is a formula for Fermi energy in terms of there is a relation which correlates the Fermi energy and density of electron. So what we will do, we know Fermi energy is the maximum energy of the electron, that is at absolute zero temperature. So at absolute zero temperature, the maximum level for which the probability of occupancy is 1 is Fermi level. So how we will derive that formula? So if we talk about density of states, now the number of electrons is given by, this is the number of electrons, NEDE equals to ZEDE. So NEDE is given as ZEDE into Fe, where this is the number of electrons. This ZEDE is the number of states at in an energy interval E plus E to E plus DE. That is, this is called as the density of states. Density of states, and this Fe is the electron distribution function, which is the electron distribution function, which is nothing but the Fermi distribution function we just talked about. So the density of states in three dimension, if you talk about the density of states, the density of states is given as ZEDE. If you are following the lectures of the course, given as pi by 2 into 8m by h square to the power 3 by 2 e to the power half dE. So in three dimension, this is in three dimension. So the relation is JD is directly proportional to e to the power half in three dimension. JD is directly proportional to e to the power, sorry, e to the power 1, sorry, e to the power 0 in two dimension, and JD is directly proportional to e to the power minus half in one dimension. So this is the basically the relation. So now in three dimension, if we plot E versus JD, then it will be somewhat like this, and this is the, suppose this is DE. So the number of levels present in the energy interval of E to E plus DE is given as JDDE. So now if we calculate the total number of electrons, so what will be the total number of electrons? The total number of electrons will be N, which will be integration of NEDE. Now if we calculate at 0K, and we know at 0K for, so now if we consider Fe is 1 by 1 plus exponential E minus EF by KBT, and also in this relation there was NEDE into JD into Fe. We got the value of JD, that is density of states. Fe is this, and we need to find out the total number of, not total number density N by integrating this right hand side. But if you see at absolute zero temperature, because in the question it says what is the Fermi energy at absolute zero temperature. So at absolute zero temperature, all the energy levels for which E is less than EF, Fe is 1, and for E greater than EF, Fe is 0. So these things I had also discussed in the last session also. You see at absolute zero, that is exponential E minus EF by 0. So if this is negative, then it will be exponential minus infinity. If this will be positive, then it will be exponential plus infinity. So if this is positive means E is less than EF, then it is plus infinity. So 1 by infinity is 0. So for E greater than EF, this is 0. But if E minus EF is negative, that is E is less than EF, then it will be exponential minus infinity. So exponential minus infinity means it will be 1. So you see, for at absolute zero temperature, all the energy levels above Fermi energy are empty, and at absolute zero temperature, all the energy levels below Fermi energy is completely filled. So for E less than EF, it is 1, and for E greater than EF, it is 0. So if we are talking about the integration, we will only take E less than EF. So the integrating limit will be 0 to EF. So here the value in place of Fu we can put as 1. So N will be 0 to EF NEDE ZE into 1. So if you put the values, since in ZE it is e to the power half, so if you integrate it, it will be e to the power 3 by 2. So if you calculate, it will be pi by 3 into 8m by h square to the power 3 by 2 into EF to the power 3 by 2. So into V. So if you take V to the left hand side, it will be N by V. That is the number of electrons per unit volume, which is the number density of electron, which will be pi by 3 into 8m by h square to the power 3 by 2 into EF to the power 3 by 2. So if you calculate it, then after rearranging, we will get EF is equals to h square by 2m 3n by 8 pi to the power 2 by 3. So this is the relation which we will use. So this is the relation of Fermi energy at T is equals to 0 Kelvin, that is absolute zero temperature. So in the question, it is given calculate the Fermi energy of electrons at 0 K for a metal with electron density of 10 to the power 28 per meter cube. So in that expression, if we put the value of N, we can easily calculate what will be the Fermi energy. So from the formula, we just calculated EF equals to h square by 2m 3n by pi to the power 2 by 3. So this is nothing but EF0. EF0 will be h square. H is Planck's constant. The value is 6.62 into 10 to the power minus 34 joule into second, which is h square by 2 into m. M is mass of electron, that is 9.1 into 10 to the power minus 31 kg into 3 into density is 10 to the power 28 divided by pi 3.14 to the power 2 by 3. So if you solve it, after calculating, we will get 2.75 into 10 to the power minus 19 joule. So correct option will be option B, that is 2.75 into 10 to the power minus 19 joule. This is the expression for Fermi energy at absolute zero temperature in terms of the density of electrons. And if we put the value of density of electrons as it is given in the question at 10 to the power 28, we can easily calculate the Fermi energy, which will be up 2.75 by 10 to the power minus 19 joule. So I hope this is clear to you. This is the basic procedure for calculating the Fermi energy at absolute zero. Jd is the density of state, Fe is the electron distribution function, and N is the total number of electrons. So Jd is the distribution function. So it depends upon the energy, and the relation is Jd right proportional to the power half. So the curve will be something like this. This is since this is the curve of x to the power half. If you calculate at absolute zero, you see if E is less than EF, so this is positive. It is for E, sorry, E is 1 minute. So if E is less than EF, exponential E minus EF by kBT will be 0. How? Because it is kp by t is infinity and exponential E minus EF is minus, since E is less than EF, so E minus EF will be negative. So exponential minus infinity is 0. So 1 by 1 plus 0, that is 1 by 1 equals to 1. Similarly, for E is greater than EF, it will be plus infinity. So 1 by infinity will be 0. Then if you put all the formulas and calculate, this will be this is the relation, and this the relation if we apply, we can easily get the answer. Then we will move to the next question. The question says silver, which has an Fc structure, you all know, we have discussed also. All the metals, mostly metals have Fc structure because uh, so in silver, FCC is one of the um, closely packed structures with relatively high packing fraction in comparison to body center cubic and uh, mm, simple cubic. So silver, which has an FCC structure, has an atomic radius of 1.45 angstrom. Assuming silver to be monovalent metal, calculate the value of Fermi velocity of the free electrons. The options are option A, 1.396 into 10 to the power 6 meter per second. Option B, 1.486 into 10 to the power 6 meter per second. Option C, 1.587 into 10 to the power 6 meter per second. And option D, 1.927 into 10 to the power 6 meter per second. So again, we will use the same formula, but here the formula was related to the Fermi energy and the number density. So since here the number density is not known, first we will calculate the number density. So we will calculate the number density of electrons, number of electrons per unit volume of silver, and then from that number density we will calculate the Fermi energy using the relation that we have just using the relation that we just derived in the previous question, and from that Fermi energy we will find the Fermi velocity Vf, which will be half mvf square. So these are the 3 steps to solve this question. So I'll give you a few minutes to solve it, and then I will be calculating what will be the correct option. So first we will calculate the number of electrons or the number density of electrons in silver. So it is given silver as an FCC structure. So for an FCC structure, the number of atoms per one unit cell is 4. So this is the FCC structure. So at 8 corners we have 8. Then on the face we have 6. So this will be 8 into 1 by 8 plus 6 into 1 by 2, 3, so total 4. So the number of atoms per unit cell for an FCC structure is 4. And in the question it is mentioned, assuming silver to be monovalent metal. So monovalent metal means each silver atom contributes 1 electrons for conduction or for uh, so so each silver atom has only 1 free electron since it is monovalent. So for 1 unit cell since there are 4 silver atoms, so there will be 4 electrons. And if you talk about the uh, uh, atomic radius, the atomic radius is 1.45 angstrom. But if you talk about the unit cell, so we know for FCC structure, if R is the radius of atom and A is the unit cell dimension, then the relation is 4R is equals to root 2 A. So A is 2 root 2 R. So the volume of unit cell will be A cube, since it is the cube of side A. This is A. So A cube will be 2 into 1.414 into R. R is also given. R is 1.45 angstrom. 1.45 angstrom. So AQ will be 4.073 angstrom cube. So if you calculate the number density, the number since mass is mass density is mass by volume, so number density is the numbers by volume. So the number of electrons per unit volume in silver atom will be calculated by n equals to 4 by the volume of the unit cell, that is 4.073 into 10 to the power minus 10 cube, that is 5.9 into 10 to the power 28 per meter cube. So the number density of the electron number density for silver is 5.9 10 to the power 28 per meter cube. So now the Fermi energy can be calculated using the formula we just discussed in the previous question. EF will be h square by 8m the formula is h square by 8m 3n by pi. So this is the formula, h square by 2m 3n by pi. sorry, 3n by 5. So it is h square by 8n. So this is nothing, it is 8n. Sorry, this is 8m. No, this is all this will be 8m, not this is 8m, 3n by pi. H square by 8m, 3n by pi. So here it will be h square by 8m, 3n by pi to the power 2 by 3. So it will be 6.62 into 10 to the power minus 34 divided by 8 into 9.1 into 10 to the power minus 31 square into 3 into 5.9 into 10 to the power 28 divided by 3.14 to the power 2 by 3, which will give you, after calculating, the 8.87 into 10 to the power minus 19 joule. So this is the Fermi energy, because all these we have converted into SI units. So it is 6.62 into minus 34 joule into second. So if you calculate, the Fermi energy will be 8.87 10 to the power minus 19 joule. Now, what will be the, let me add another slide. So we know half m Vf square is equals to Ef, which is 8.87 into 10 to the power minus 19. That implies Vf equals to 2 into 8.87 into 10 to the power minus 19 divided by 9.1 into 10 to the power minus 31 meter per second. So it will be 1.396 into 10 to the power 6 meter per second. So this is the answer. It is 1.396 into 10 to the power 6 meter per second. So the correct option will be 1.396 into 10 to the power 6 meter per second. That is option A. So option A will be the correct option. The Fermi velocity of 3 electrons in silver atom with an atomic radius of 1.45 is 1.396 into 10 to the power 6 meter per second. Now, question number 6. Aluminum metal crystallizes in FCC structure if each atom contributes single electron as free electron and the lattice constant is 4.2 angstrom. Calculate the Fermi wave vector kf for free electrons. Consider the reduced Planck's constant, that is h cross equals to 1.054 into 10 to the minus 34 joule into second. Options are option A 1.16 into 10 to the power 10 meter per meter. Option B 7.73 into 10 to the power 9 per meter. 2.14 into 10 to the power 8 meter inverse, and option D 8.92 into 10 to the power 7 meter inverse. So again, this question we also use the same formula. We will first calculate the density, then we will calculate the Fermi energy from the electron density, and from that Fermi energy we will convert it into Fermi momentum, and we know Fermi momentum is nothing but h cross k. So h cross k, Pf is h cross kf. H cross value is given to us, and we need to find out the Fermi wave vector kf. So I'll give you a few minutes to try this question, and then I will discuss. So if we do like the previous question, so again, since aluminum is assumed to have an HCC structure, N is equals to 4, and it is 4.2 Armstrong. So here you see, in the previous case, the atomic radius was given, but here the lattice constant is given. So very simply we can calculate. This is, suppose this is N A, that is number of atoms per unit cell. So the number density of electron will be 4 by volume of unit cell, that is 4.2 Armstrong cube. That is 4 by 4.2 into 10 to the power minus 10. So it will be 5.4 into 5.4 into 10 to the power 28 per meter cube. So now the Fermi energy EF will be given by a square by 8m 3n by pi to the power 2 by 3. So this is 6.62 10 to the power minus 34, 8 into 9.1 into 10 to the power minus 31 square, then 3 into 5.4 into 10 to the power 28 divided by 3.14 to the power 2 by 3. If you calculate, EF will be EF will be 8.36 into 10 to the power minus 19 joule. Now we know if PF is the Fermi momentum, then EF is PF square by 2m. So PF square will be 2m EF. That implies PF will be 2m EF root over. That is 2 into 9.1 into 10 to the power minus 31 into 8.36 into 10 to the power minus 19 root over equal to 1.23 into 10 to the power minus 24 kg into meter per second. Now, if you calculate the Fermi wave vector, that is kf, so Fermi wave vector kf will be So H cross Kf will be Pf. That implies Kf will be Pf by H cross will be 1.23 into 10 to the power minus 24 divided by 1.054 into 10 to the power minus 34. It is 1.16 into 10 to the power 10 meter inverse. So the correct option is 1.16 into 10 to the power minus 10 meter inverse. That is option A. This question is pretty much similar to the previous question, but here we only the last step is different. We only calculated the value of Fermi momentum. So first we calculated Fermi energy from the density of electrons. Then from that Fermi energy we calculated Fermi momentum, and then we calculated the Fermi wave vector. I hope this is clear to everyone. Then we will move to the next question. The question says calculate the Fermi energy of potassium, which is assumed to be having an body center cubic structure at 0 Kelvin, and the lattice parameter of potassium is 5.3 angstrom. So here you should note, here the lattice parameter is given. The lattice parameter means A is given. We don't need to convert the lattice parameter into, we don't, so in some question there is atomic radius is given, so you have to put the relationship between atomic radius and the lattice parameter in order to find the volume, because the volume of cubic unit cell is AQ. So if R is given, so you need to convert R into A, then we will find the volume. But here, if you see, the lattice parameter is already given, which is 5.3 angstrom, and we need to find out the Fermi energy. Assume each atom contributes single free electron. So this is a pretty straightforward question. We will only find the Fermi energy. So first we will calculate the electron density, that is the number density n, and then by using the same formula we will calculate the Fermi energy, that is EF. The options are option A 1.02 electron volt, option B 2.06 electron volt, option C 3.18, and option D 4.02. So if you see in the previous questions, all the energies were calculated in terms of joule. So since here the option given in terms of electron volt, so we will convert joule into electron volt. So I'll give a few minutes to try this question, and then I will discuss what will be the correct option out of these four options that is given in the question. So since it is BCC structure, then for BCC structure N is equals to 2, number of atoms per unit cell. So the number density will be 2 by AQ, that is 2 by 5.3 into 10 to the power minus 10 cube. It will be 1.34 into 10 to the power 28 per meter cube. Then Fermi energy at 0K will be EF0 equals to x square by 8m 3n by pi to the power 2 by 3. That implies 6.62 to 10 to the power minus 34 square divided by 8 into 9.1 into 10 to the power minus 31, 3 into 1.34 10 to the power 28 divided by 3.14 to the power 2 by 3. This is 3.3 into 10 to the power minus 19 joule. So in order to convert it into electron volt, so we will divide it by 1.6 into 10 to the power minus 19. It will be converted into electron volt, which will be 2.06 electron volt. So the correct option is option B, that is 2.06 electron volt. So this question is so all these few questions that we are solving from past few minutes are pretty similar to each other. We only need to find out the number density, and then from that number density we will find out the Fermi energy, and then from that Fermi energy different quantities can be calculated using different formulas. Again, this question is pretty much similar. The question says the density of potassium is 861 kg per meter cube. Calculate the Fermi energy of potassium at 0 Kelvin. Atomic mass of potassium is given 39.1 gram per mole. We need to assume that each potassium atom contribute single conduction or free electron. Options are option A 3.28 into the minus 19 joule, option B 1.27 into 10 to the minus 21 joule, option C 1.38 into 10 to the minus 23 joule, and option D 4.22 into 10 to the minus 27 joule. So here similarly we will calculate the number density n, but here since the structure is not known to us, and also the lattice mm, dimension, that is the unit cell dimension, or nor the atomic radius is given. So here we will use another formula for calculating the number density, which will be in terms of mass density and the molar mass or atomic mass of potassium, that is 39.1 gram per mole. So we will calculate, and we'll from that density of electron we will again calculate the Fermi energy like the previous questions. So I'll give a few minutes to try this question, and then I will discuss what will be the correct option. So in order to calculate the number density, we will use the formula n equals to d n a by m, where d is the mass density, that is 861 kg per meter cube. N is the Avogadro's number, that is 6.023 into 10 to the power 23 number of molecules per mole. Then M is 39.1 gram per mole, which will be 0.0391 kg per mole. Or we can say 39.1 into 10 to the power minus 3 kg per mole. So if you put all these values and calculate, then N will be 861 into 6.023 into 10 to the power 23, 39.1 into 10 to the power minus 3, which will give you, after calculating, 1.326 into 10 to the power 28. Then the Fermi energy will be 6.626 into 10 to the power minus 34 square divided by 8 into 9.1 into 10 to the power minus 31 into 3 into 3.31.326 into 10 to the power 28 divided by 3.14 to the power 2 by 3. Then it will be 3.28 into 10 to the power minus 19 joule. So this is the answer. Correct option is 3.28 into 10 to the power minus 19 joule. That is option A. So we will calculate. We first calculated the number density of electron from mass density and atomic mass. Then we calculated the Fermi energy using the formula. Similarly, we will move to the next question. That is question number 9. The question says the energy dispersion of the conduction band of a one-dimensional metal is given by EC, which is the function of kx, is Eg. Is the forbidden energy gap, plus E1 sine square kx a by 2, with h cross kx is the crystal momentum, a is the lattice constant, Eg and E1 are constants. Compute the effective mass of an electron at kx equals to pi by a. So E is given. E is the function of kx. It is given to us. We need to find out the effective mass, which is called as m star. The options are option A 2h cross square by E1 a square, option B minus 2h cross square by E1 a square, option C h cross square by E1 a square, and option D minus 3h cross square by E1 a square. So this question is based on the band theory of solids. So I will give a few minutes to you to try this question, and then I will discuss. And I will also discuss about the effective mass. Why effective mass is important. So the expression for EC as a function of kx is given, which is Eg plus E1 sine square kx a by 2. And we know the formula for effective mass is m star equals to h cross square divided by delta square EC by del kx square. So del EC by del kx will be 2 U1 sine kx a by 2 into a by 2 into cos kx a by 2. Then delta square EC by delta kx square will be E1 a by 2 cos k1x a into a. So this will be 2 sin theta into cos theta is equals to sin 2 theta. It will be E1 sin k1x a into a by 2. So if you again take the derivative, it will be a by 2. So it will be E1 a by 2 sin k1x derivative cos k1x into a. So we need to put the value of kx pi by a. So m star will be h cross square divided by del square EC by del kx square, that is 2h cross square divided by E1 a square cos k1x a. So putting kx as pi by a. So cos pi, we know cos pi is minus 1. So it will be minus 2h cross square divided by E1 a square. This m star, that is the effective mass of electron. So the correct answer is option B, that is minus 2 h cross square by E1 h square. So here you see the effective mass can be negative also. So when an electron moves in free space or outside of an uh, or the free electron, we can say, then the mass of the electron remains constant, which we all know, that is 9.1 10 to the minus 31 kg. But how the electron behaves inside the crystal, so depending upon its position, the mass of the electron can be positive or negative. So the mass of the electron while moving inside the crystal varies. It is not constant throughout its presence. So that mass is called as effective mass, and effective mass plays an important role in calculating some of the properties, and also some devices that are being made are also based on the principles of effective mass. Now question number 10. The question says a hypothetical semiconductor has a conduction band that can be described by E c function of k is E1 plus E2 sine square Ka, with A is the lattice constant and E1 and E2 are constants. Now calculate the groove velocity of the free electron at the conduction band edge. So here also say the at the end of the conduction band. So in the previous question that was kx equals to, so here it was compute the effective mass of electron at kx equal to pi by a, but here it is given calculate the group velocity of electron at the conduction band edge. So at the edge of the conduction band, we know the value of k is 0 at the edge of the conduction band. So like to the previous question, we know the group velocity in terms of can be represented in terms of derivative of the conduction band energy, that is 1 by h cross del ECK divided by del K. So we know del EC by del K will be 2E2 sin Ka into cos Ka into A, which is E2A sin 2Ka. So group velocity Vg will be E2A by h cross sin 2Ka. So at the band edge, that is K equals to 0, Vg at K equals to 0 will be 1 by h cross del ECK by del K at K equals to 0. And we know sine 0 is 0, it will be 0. So the group velocity is 0 at the group velocity is 0 at the conduction band edge according to the relation given by the conduction band energy relation. So the correct option will be option B. So the question was, for a hypothetical semiconductor, a conduction band was described by a relation EC equals to E1 plus E2 sine square Ka, where A was the lattice constant, E1 and E2 are constants. So we need to find out we need to calculate the group velocity, and we know the group velocity is given by 1 by h cross delta EC by del K. So if you calculate and put the value of K at the edge of the conduction band, that is 0. So the group velocity will be 0. So I hope this is clear to you. Then we will, so with this we come to the end of today's interaction session. In the next interaction session, we will solve a few problems that will be based on the week 9 of the course solid state physics, which will be based on thermal properties of solids. We will discuss about how the electrons contribute to the thermal property as well as the phonons, because but during the electrical property, since only electron can conduct electricity, only electrons are playing a role. However, in case of thermal property, however, in case of thermal property, both electrons as well as phonons will contribute. So we will discuss about these things and we will solve a few problems that will help you in solving the assignment problems are also for appearing in the exam if you are registering. So with this, I come to the end of today's session. Wish you all the best for your course.